In supervised machine learning, the objective is straightforward. We use historical training data to build a model that predicts outcomes for new, unseen information. When the required output is a continuous numerical value, the process is known as regression. This chart outlines the mechanics of that process. Look at the dependent variable. If we provide predictors like a mother's height, a father's height, and a child's age, a regression model calculates a precise numerical output, the predicted height. But as this slide shows, classification is used when the output is a discrete category, or a label. Instead of calculating a point on a numerical scale, the model sorts data into groups, such as buyer or non-buyer. Because classification handles discrete categories instead of continuous variables, it uses different mathematical mechanics than a standard regression line. Sorting outcomes into distinct groups requires a different structural approach. Classification models rely on features. These are the independent input variables, such as a person's age, gender, or the frequency of specific words in an email. The model then attempts to assign a label. This is the dependent categorical output derived from those input features. This list shows how multiple features combine to define a single label. For example, an email filter analyzes keywords to assign a label of spam or not spam. A medical model uses age and history to assign a disease label. There is no single equation for mapping these features to labels. Instead, algorithms generally rely on three distinct mathematical frameworks: spatial proximity, hierarchical logic, and probability. To turn raw data into a category, a model must adopt a structure that matches how that data is organized. We can see how this works by looking at each framework individually. The first framework is spatial proximity, used by the k-nearest neighbors, or KNN, algorithm. Look at how KNN defines its core mechanism. It treats feature values as coordinates and defines similarity as the physical distance between those points. We can plot a dataset, like city temperatures, onto a coordinate plane. Here, cities labeled cool, warm, or cold are placed according to their latitude and longitude. When we introduce a new, unlabeled city, the algorithm uses the Euclidean distance formula to calculate the exact gap between the new point and the existing data. The k represents the number of closest items the algorithm must find. If k is 5, the algorithm identifies the 5 nearest neighbors on the grid. The new item is then assigned the label that appears most frequently among those 5 neighbors. K-nearest neighbors assumes that items with the same label will naturally cluster together in a multidimensional space. The second framework, hierarchical logic, is used by decision trees. This method discards spatial distance. A decision tree maps features to nodes and values to edges. Instead of mapping data on a grid, it asks a sequential series of questions. A data point navigates this network based on its specific values. For instance, it might pass the female edge, hit an income node, and then follow a path based on whether the value is above or below $100,000. The path ends at the leaf node, where the final categorical label is assigned to the data point. This approach can be vulnerable to rigid thresholds. A single split that is slightly off can miscategorize data that falls near the boundary. To increase accuracy, data scientists often build a forest of many distinct trees and combine their results. Decision trees are used when data can be divided by clear logical roles rather than spatial clusters. The third framework uses statistical probability, executed through the naive Bayes algorithm. Rather than finding neighbors or following paths, the model calculates the probability of every possible label and selects the one with the highest percentage. This matrix shows how the algorithm computes the fraction of items in a category for each feature, like checking how often a city on the coastline is labeled warm to build its mathematical case. For this calculation to be fast across large datasets, it relies on a mechanism called the conditional independence assumption. Conditional independence assumes that, given a specific label, the probability of one feature is completely isolated from the probability of any other feature. This is described as naive because features like income and postal code are often connected in the real world. Even though it simplifies reality, naive Bayes is computationally efficient, making it a standard choice for high-volume tasks like email spam detection. We can compare these three models by using them to solve the same problem, diagnosing a patient based on raw symptoms. KNN processes the patient by mapping their symptoms onto a coordinate grid to find the nearest match among previous patient records. A decision tree evaluates that same patient by routing their symptoms through a series of threshold queries. And naive Bayes diagnoses the patient by multiplying the independent probability weights of each individual symptom. Despite using different internal mathematics, all three frameworks arrive at the same output label. Selecting an algorithm depends on how your data is structured, whether it clusters spatially, splits logically, or requires probabilistic weighting. Understanding these mathematical frameworks allows you to select the right tool for the specific nature of your data.